Good morning. It's about 3 o'clock a.m. where I came from, so it's probably perfect time. So I didn't know about anything about curriculum, so what I thought to do is introduce photoacoustic imaging in terms of principles, in terms of hardware and how do you approach doing photoacoustic imaging, and show you some typical applications, but very small number of them. My name is Stas Emelianov. I am from the Department of Biomedical Engineering at UT Austin. I also have appointment in imaging physics at MD Anderson Cancer Center. So examples I will give you will be primarily related to cancer just because that's something I'm more familiar, although we have a massive research project in atherosclerosis and imaging blood vessels. So starting with history, photoacoustics. It really was introduced by Alexander Bell in about 1880s. What he said is he really invented the first wireless phone. He realized that he can transmit, or he would like to transmit sound over large distances, but that wouldn't work, even if you yell. And so what he suggested is to encode sound in form of modulated light. And so he came up with the photoacoustic phenomena in the device he called Photophone. When you will talk, that will be recorded as modulation of light, and then that light can propagate over large distances using simply ray propagation, and then will be kind of transformed from light back to sound at the other end. Obviously that technology didn't take off, but he was clever enough to describe all the principles of photoacoustics and the ones that we're going to use today. Now, starting from that time, really the birth of the biomedical photoacoustic imaging was in 1981 when Theodore Bowen suggested that we can use some form of electromagnetic radiation, including light, to produce images, relevant images of biological tissues. And then seminal work, I can't really list all the researchers working in this field. It's largely exploding right now. It's undergoing its second renaissance, if you wish. But a few people, Orayevsky, Steve Jacks, Diebold, Paul Beard, Robert Kruger, those were the people that were at the beginning of this field. And now there's many, many more people, and you can actually, probably you cannot tell, but my name is not listed there. We came to this field roughly in 2002, 2004. Now, another interesting point to note on this slide, I'm trying to compare ultrasound, but I can put pretty much any imaging modality such as CT, MRI, whatnot. When we discovered the effect and start sort of developing, immediately went to clinical systems. And then later on, preclinical systems were invented. Photoacoustic imaging kind of reverting that history. We now have many preclinical systems. In fact, we have 3, if not more, but the clinical photoacoustic systems are not yet available. They are under development, and I hope soon they will be introduced to clinical practice. So like I said, I cannot really represent the work of many individuals working in this field. So what I thought to do is actually focus on preclinical photoacoustic imaging and actually show you examples that are produced by the 3 manufacturers of those preclinical photoacoustic imaging systems. Now, if you're going to leave in the next 5 minutes and don't listen to the rest of my talk, at least one thing you would remember, photoacoustic imaging, which is also optoacoustic imaging or thermo-acoustic, the simplest way to think about it is lightning and thunder. There's nothing more to it. So in this particular case, right, we have a lightning bolt, which is the form of electromagnetic energy. It interacts with the atmosphere being air. That air, because of interaction, will be very quickly heated up. There will be some deposition of the thermal energy, and because of that, because it's a rapid event and rapid deposition of the thermal energy, the air around lightning bolt will expand, it will produce sonic boom, and then all you have to do as a Boy Scout or Girl Scout is count. In where I came from, we count until 3, that corresponds to 1 kilometer. Where I went to, which is United States, we count until 5, because that would correspond to 1 mile. But the point is very simple. You hear the effect, you listen to it, you count seconds that tells you how far the event is from, and based on the amount of sound you receive, you will realize how drastic that event is, right? So very simple, lightning, and through the thunder, you can estimate both the strength and the location of the event. We're going to use exactly the same, except for biomedical purposes. So our lightning will be laser pulse that we're going to introduce into the tissue. By definition, the tissue will have optical absorber located somewhere inside. We don't know where, but we assume it's there. Now, what's going to happen with the light as it propagates through roughly 0.5 millimeter of the tissue, it will propagate in straight lines, and previous speakers described that well. But then as soon as it kind of reaches that limit of ballistic propagation of photons, it will be scattered, and the rest of the photons will still propagate into the tissue. But they will scatter, they will lose their identity. You cannot tell where they're coming from or where they're going next. Primarily would be forward scattering, but again, the identity would be lost. Nevertheless, starting with the initial number of photons, we certainly will deliver some photons at the sufficient depths. It will be determined by effective coefficient, which combines both attenuation and absorption in the tissue itself. So if we pick particular wavelengths of optical light, we can actually penetrate up to 5 or even 7 centimeters of tissue, but in the scattered light, which means optical imaging would not work. The photons are scattered, and optical imaging at this depth would be very hard to do, or you can do images, but they will lose spatial resolution. So that's the step number one. Step number two, again, remember the analogy with lightning and thunder. Once the photons will reach the optical absorber will, by definition, it's absorber, it will convert the energy from electromagnetic to thermal, right? Which means very small deposition of temperature will take place. That deposition of temperature is a small fraction of the degree, so there should not be any thermal concerns or thermal damage, if you wish. However, even the deposition of the temperature is very small. There will be large stresses generated especially at the surface of the absorber, because tissues are incompressible, and no matter how small the temperature is, it will expand and generate acoustic waves. So that's the third step in photoacoustic imaging. And fourth one is, because of the stresses produced, it will generate acoustic boom. From a particular absorber shown here, it will be spherical wave emitted in any direction, and all you have to do now is start listening, right? You will listen first for the amplitude of photoacoustic wave, right? The stronger that amplitude is, the stronger the optical absorber is at particular depths. And second, you will be listening at what time this particular echo arriving to you. That will tell you the distance between the optical absorber and the acoustic detector. So in principle, it's a very, very simple technology, lightning and thunder, where we can produce depth-resolved photoacoustic images where contrast is primarily determined by optical absorption, not optical scattering. I do need water in my water cup. Thank you.
It's good that you asked. You're the only one.
Yeah. I asked earlier. So photoacoustic imaging system, the simplest way to do is you take an expensive laser pointer, shown here, right? The reason it's expensive because A, it operates in a pulsed mode, and B, it can change the color, right? We would like to vary the color of light. And then through fiber optics, you will put that light at the tip of the ultrasound transducer. Now, if you ask me, where do you get the ultrasound transducer? It comes with ultrasound imaging system. So that's what you would do in most cases to build photoacoustic system in your own lab. You would take the ultrasound imaging system, which consists of ultrasound transducer, and add laser source and integrate those two components together to produce images. So usually it makes sense to combine it with ultrasound simply because the receive component of the ultrasound imaging system is about 95% of the cost of that system. And so you add laser pointer and you got yourself photoacoustic imaging system. So this is the diagram, but what could happen in reality is shown here. Right, this is not work from our lab. In fact, I'm trying to stay from examples from our lab. This has been done in Switzerland. You see the ultrasound transducer, you see red color, that's the color of the light. It's just for demonstration purposes. And this is the typical ultrasound system. You see the ultrasound image in the background, and then photoacoustic signal showing the blood vessel displayed on the top. And this is the schematic diagram. Again, you have ultrasound transducer, you bring the light through optical fiber, you kind of distribute it around the transducer in illuminate area underneath. But the very important point here is you get 2 images for the price of 1. Right? You get photoacoustic image, you get ultrasound image, and guess what? How do you correlate them spatially? You don't need to do anything, you just assemble that in PowerPoint, because these images are acquired by exactly the same sensor, which is ultrasound transducer, so it's always seeing everything from its own and unique perspective, which means images will be spatially co-registered. They temporally consecutive, but spatially they come from exactly the same portion of the tissue. So you don't need to do any image co-registration, it's naturally given to you by this technology. Okay, talking about the manufacturers, right? Because I'm trying to stay away from research systems and from contributions that every research group made. There are 3 of them as far as I can tell. I checked last night, all of them should have their presence at this conference. Andra, that produces Nexus 128, Visual Sonics, that makes Vivo laser system. And in fact, that's the system we have in the lab. And the third one will come from iThera Medical. They call it MSOT, which is also listed here. Now, on the top, and remember, these images are not to scale, right? I don't want to say this is a much bigger system and this is somewhat smaller. You will look at it starting at 7 o'clock today, if you wish. But generally, each one of those systems will have combination of ultrasound sensor and laser source. Right, it's either combined in one box. Here you can see actually 2 separate boxes. Visual Sonics was making ultrasound systems for a long time, and then they just added laser source and integrated all into the same package, and that's the Photoacoustic / ultrasound system. iThera, again, you have all of those components inside of this box. Now, if we open the hood of that system, this is what we're going to see inside. In this case, the light comes from the optical fiber, illuminates the mouse or small animal, located here, and then the ultrasound sensors will be located all the way around this particular arc. In case of Visual Sonics, they use typical ultrasound transducer, and I was not able to get their image. This is our own SolidWorks interpretation of that. This is the ultrasound transducer. It has ultrasound elements at the tip. This is, again, typical clinical or preclinical ultrasound system. And they would add optical fibers on each side such that they can illuminate tissue underneath and detect that. And this is their optical enclosure with the transducer shown here. Now, in case of iThera, the transducer is more of just half of the arc. It's located all the way here. And the optical illumination comes from the fiber located over there. And then the mouse will be positioned here and scanned sort of longitudinally, if you wish, or 3-dimensionally by moving mouse or disassembly in Z-axis, as we've done in CT or MRI, if you wish, although in MRI we don't move patients. In here, what you would do is this transducer will collect this plane, imaging plane, and in order for you to produce 3D image, you will simply move that transducer in the Z direction as well, right? So that's how those systems work. Now, you probably will see similarities between those systems. Laser and ultrasound in all of them. All of them are capable of producing 3D images. Now, the difference would be this is a little bit more of tomographic or full angle view of the system, but it comes at its own expense. And this would be similar to MSOT. Vivo laser is built on top of the ultrasound system, so it does give you both images at the same time, but they will be sort of from a limited angle perspective in terms of reconstruction. If I have time, I come back to that. Okay, why do they bother making those systems? In addition of making money, I think that's one of the goals that the industry would have, but why bother? The reason they bother is if you look at the sort of beauties or pros and cons of each imaging system or each, at least, energy domain, you would realize in ultrasound, we make images in real time. We're doing a great job in terms of anatomy and structure. We can visualize things at sufficient preclinical and clinical depths with reasonable spatial resolution. What we cannot do in ultrasound is contrast is hugely limited. It's practically related to anatomy and structure. We're not sensitive to the events at molecular level, cellular level, And our contrast agents on the micrometer scale, which means they're primarily going to remain in vasculature and barely interact with the tissue otherwise. When I go to light or electromagnetic wave imaging, I see excellent contrast and resolution. I see sensitivity to physiology and molecular cellular events. I see nanoscale contrast agents. Dyes would be a simple example. They are very small molecules. The problem with imaging with light is very shallow penetration of ballistic photons, and therefore you cannot image events at sufficient depths. Right? However, if you look at those kind of side by side, you realize pros and cons are counteracted. Right? Penetration depth is very fantastic here, and it's very small here in terms of ballistic photons. If you look at sort of sensitivity to events that, especially at this conference, might be of interest, light does great job and ultrasound kind of suffers. And that brings me to a very simple point that I can actually combine light and sound and eliminate all the cons, leaving all the pros on the table. Right? So hopefully by appropriate combination of those two technologies, I can image in real time at sufficient penetration depths with optical contrast, but at ultrasound resolution, which would be sub-millimeter scale. But what's more important, perhaps, is I can now visualize all possible events happening in the body, ranging from anatomy all the way to physiology, all the way to functional biology, if you wish. Right? By definition, this photoacoustic imaging combination light of sound can be multimodal. I can combine it easily with ultrasound. There are work that's done in combination with OCT and other optical technologies. And again, my contrast agents, which will enhance any particular molecular or cellular signature in the tissue, could exist anywhere on the sub-millimeter to nanometer scale level. Right, so all of that is very exciting. Okay, if I sort of summarize photoacoustic imaging briefly and remember those 4 steps, illumination with light, temperature deposition, expansion, thermal expansion, and production of photoacoustic signals, we can talk a little bit about physics, although I don't want to do that. One perhaps that I really don't want to address is the temperature elevation, and should I be concerned about thermal damage and safety. In my lab, whenever we're testing the system, I usually stick my hand in the laser beam, and so far it's still with me. So there's never been done any thermal damage. And again, if you go through equations or through modeling or through direct measurements of the temperature deposition is extremely small, extremely small. Perhaps what I want to do, actually, I don't want to go through this list, maybe talk about laser pulse duration and choice of the optical wavelengths. What do you expect? What kind of laser pointer you should buy? First of all, let me remind you that the contrast mechanism in photoacoustic imaging is absorption driven. By the way, this particular contrast mechanism is not duplicated by any imaging modality technology that we know of today. Look at even optical imaging, which is primarily index of refraction or derivatives of that, right? And of course, anything else would be as far away from optical contrast as possible. And so it would make perfect sense for us to look at the optical absorption coefficient as a function of the wavelengths, and we can make some discoveries here. Number one is, of course, my contrast in photoacoustic imaging is based on the absorption, which means if absorption doesn't change, I'm not going to image anything important. However, what I cannot allow in this imaging technology is absorption to be too high, because then the light will not penetrate deep into the tissue, it will be absorbed superficially. So if I look at the broad spectrum of optical wavelengths, I really need to be somewhere here. In what we call optical window of the tissue, it's ranging between 650 to maybe 1300 nanometers, but that is sort of loosely defined. The reason we don't want to be in this range is because every micromolecule in the tissue will absorb badly, which means, again, no penetration. The reason I don't want to be here, and even in maybe 1100 nanometer wavelengths, because not many things absorb and there's pretty much no contrast. The blood, whether it's oxygenated or deoxygenated, will kind of flatten, and my images will look just uniformly gray, if you wish. They will show me no contrast. So if you're interested in blood, you probably will image in this wavelengths or optical wavelengths range. And if using contrast agents, you probably would like to go to larger near-infrared wavelengths because the tissue itself will not be on your way. But if you go even further, then the water starts absorbing too much, and so you're not going to see anything. So this is where you're stuck, right? And not surprisingly, manufacturers of current photoacoustic imaging systems will use this wavelength range as part of their imaging system. Okay, how do we generate photoacoustic signal? There are many ways of generation of photoacoustic signal. The one that we currently use is done through absorption, thermal deposition, and thermal expansion of the tissue. Yet there are 3 other mechanisms that are possible. If I look at the physics, again, something very interesting. Again, there are many types of the interaction of laser with tissue, but all of these interactions simply depend on a single parameter, which is the duration of the laser pulse. Short duration, you have photothermal, photochemical interaction. Short duration, you have photoacoustic, photodisruption, plasma-induced ablation, and photoablation, if you wish. So all of this depends how short or how long is your optical pulse. And also something to notice, power density, as you go sort of through this range of interactions, varies by 15 orders of magnitude. This is just to notice. Now, what's the length of the pulse? Well, first of all, you probably can recognize if I just shine the light at the tissue, it will not produce photoacoustic signal because there's no rapid expansion of the tissue. You're just continuously heating it, and so it produces no signal, right? So in order for me to create photoacoustic signal, I have to use pulsed radiation. The first sort of criteria to achieve photoacoustic signal will be to satisfy thermal confinement, which means the effect needs to be localized and thermally not to diffuse too far away from the origin. That brings me to the 10 to the minus 3, which is a millisecond range, right? That's where you're going to start producing photoacoustic signal. So if you are on the market for your own photoacoustic imaging system and you buy CW laser, you can ship it to me because you cannot use it for photoacoustic images. It just does not produce photoacoustic image signal. It needs to be in a pulse mode. Now, if you want to use the best of the photoacoustics, you have to satisfy second criteria, which is called stress confinement. Basically, do not allow tissue to relax. And so everything that it has as an energy, it will output in terms of sound, not in terms of relaxation, which is more mechanical. And this is where you will be constrained by the nanosecond pulses. And that happened to be the laser source that you would need that is capable of producing nanosecond duration of pulses. If you go with the femtosecond lasers, first of all, it's much more expensive, and second, it doesn't give you anything because, yes, you satisfy this criteria, but the energy that you will be depositing will be so small that your photoacoustic signal, again, will go down. So it happened to be that this is the sweet spot for photoacoustic imaging, and in fact, plenty of lasers do exist in that particular domain. Nd:YAG lasers, pulsed Nd:YAG, Q-switch lasers would be one very typical choice. Now, that also brings me to another simple, actually, relationship is since you have to use nanosecond pulses because those are the optimal for production of photoacoustic signal, there's also a relationship between the pulse duration and what kind of targets you can visualize, right? And I don't want to go through the math, but simply saying for 40 nanosecond laser pulse, you should be able to visualize 16 micron targets, right? And that gives you some sense of sort of what the possible resolution, spatial resolution in photoacoustic imaging would be, although it is, of course, determined by ultrasound detector as well. So if you have a very bad ultrasound transducers, that resolution will be just ruined. So what the spatial resolution is determined at large depths, primarily ultrasound transducer, assuming you got nanosecond laser pulse. It's frequency bandwidth, or how short the pulses you can detect. It's sensitivity, which usually goes against the bandwidth, so there's always trade-offs. You want a higher sensitivity, your bandwidth will not be as great. It's a focusing, which is simply large numerical aperture if I speak optical language, or low F number if I speak ultrasound language. And of course, whether I use single element transducer versus array, and we've heard before that focusing will be much more versatile if you use array of transducers. We already discussed that the laser pulse duration will determine your resolution as well. And of course, there are practical issues such as speed of sound. If it's not uniform, it will affect your resolution. So there are always trade-offs in here. Now, looking again at those three systems, I would claim that their spatial resolution should be on the order of 100, 150 micron. Again, it depends on what transducer you use, what particular implementation you got, and also how do you reconstruct the images, because once you collected the raw signal with reconstruction, you're just hoping to preserve that spatial resolution, but you might also sacrifice it. Now, all of that was at sufficient depths, which is kind of larger than 0.5 millimeter. If you go at the low depths, which is below 500 micron, then the resolution is determined by the laser beam. An example from Li Hong Wang group is shown here, where they took the optical beam, split it to go around the transducer, and sharply focus underneath. Now, this light does not scatter because it's in the very shallow depths. And so if you're capable of focusing your optical beam very sharply, then the ultrasound transducer doesn't matter anymore, because the overlap between the two beams will determine your resolution. Right, and normally you have much easier task to focus light rather than sound, just given the wavelengths that we work with. Simple Rayleigh criteria will govern this. Okay, now image reconstruction, we have techniques in photoacoustic imaging, which is optical absorption. We can actually borrow a lot of the technologies we developed simply from the ultrasound. The task is exactly the same, except we're reconstructing something else, because that's what the contrast mechanism is. Right, there's differences and similarities, and I can give you 65 at least publications on this topic if you're interested to read. But let me tell you that probably these four are the most commonly used reconstruction techniques. Simple back projection, filtered back projection, that's a CT language. Delay in some would be language of the ultrasound reconstruction, Fourier reconstruction, more of optics. All of them are somewhat similar and have little niches that they perform better in one case than the other. And it's a very active area of the research. So I don't want to, unfortunately, talk too much more about that. Well, and again, you will see that here I have a more coverage with my ultrasound transducer, so I probably can do the filtered back projection. And here I have a very limited angular view of the object, so I will play some other tricks to come up with the reconstructed image. Temporal resolution, I think I'm running out of time, more likely, but temporal resolution will be real time, which means video frame rate. And I don't need to go through that much more. Now I want to switch to applications. And maybe what I will walk you through is what's the role of photoacoustic imaging in either management of the disease, if you are a clinical individual, or maybe in studying some fundamental principles biology, if you're more of the preclinical scientist. So what I'm plotting here is sort of the stages of the disease and what will be required from imaging. So we start with the detection of the disease, characterization, treatment, and then we would like to monitor what we've done to it, right? So that would be the progression of the management of the disease in clinical practice, if you wish. In terms of imaging, as we visualize those effects or events, as we detect the tumor, in case of cancer, as we treat it, we would like to see anatomical features of that tissue with the disease located somewhere inside. We would like to look at the functional, physiological sort of properties of that disease, and certainly identify molecular cellular composition as we detect and as we treat the disease. Now, in terms of cancer, it might be very important to identify presence of the hemoglobin, right? Because aggressive cancers will consume hemoglobin because that's what brings nutrition, if you wish, to them. And so if I'm interested in concentration of hemoglobin, I might just simply pick this wavelength, which is roughly 800 nanometers, where either state of hemoglobin absorbing exactly at the same rate. right? So I can make photoacoustic images at this wavelengths and come up with the concentration of hemoglobin. If I'm interested more in metabolic processes associated with the tumor growth and response to therapy, I might introduce another wavelength, somewhere where oxygenated, deoxygenated hemoglobin are no longer the same in terms of absorption, so that I can measure two quantities and reconstruct what's called oxygen saturation, together with the total hemoglobin, because now I have two measurements, two unknowns, should be able to solve it. And I'm going to walk you through images more or less representative from three manufacturers. These images are from Visual Sonics. You can see the abdomen of the mouse or rat, mouse abdomen, and you can see the vascular network, right? This blood does not need to move, unlike an ultrasound, for us to detect it. All it has to do is absorb light and produce photoacoustic signal. Now, if I'm not only interested in the blood in terms of vasculature, but also interested in the total hemoglobin concentration, as described before, I can start looking at the tumor and visualize where that stagnant or floating blood is. If I use a couple of wavelengths, I can make images of the oxygen saturation. Those are two-dimensional images, and again, this technology is easily extendable into 3D, where you scan the transducer, and those are the 3D images of similar tumor. That's the example from Visual Sonics. If I go to Andra, another manufacturer of photoacoustic imaging system, what they shown on their website, I simply stole those images, actually all images from corresponding websites. This is the tomographic view of the tumor located right here. That's tumor, of course, in the mouse. It's a xenographic, I believe, model. And what they do is they, same as everyone does, scan at different wavelengths and start sort of matching with the known spectra, optical absorption spectra of hemoglobin. And of course, they can reconstruct concentration, total concentration of hemoglobin, or the oxygen saturation. And again, you can see the representative images from the company working together with researcher from Purdue. But what also they've done is they look at the tumor response in terms of hemoglobin content as they sort of start treating the animal. And you can see that control, the total hemoglobin will increase nearly linearly, versus when you start treating, then at some point that hemoglobin will increase, which indicates that the tumor did respond to therapy. Right, so that would be one example how photoacoustic imaging can be used to visualize physiological events taking place in the tissue. And this is example very similar from iThera Medical, where they look at these tumor xenographic model, day 5 all the way through day 16, and the color coding here is that deoxygenated and oxygenated blood or hemoglobin is depicted in red or blue, or vice versa, right? And again, you can see the progression of the both anatomical images obtained using photoacoustic technology and the blood oxygenation. And again, these images should be correlated 1-to-1 because they were obtained with exactly the same sensor. Now, back to my diagram, which is disease versus imaging. Clearly, photoacoustic imaging or technology can visualize anatomy and functional or physiological state of the tissue. Again, all the examples are from corresponding 3 manufacturers. And in fact, I can take that example and say it's not only photoacoustics, but even ultrasound can help. Ultrasound is actually very good at visualizing anatomical features. You can see the rear end of the mouse. Here's the tumor. Here's the cross-section of the same mouse. And this is images from our lab, actually. And we collected sort of the hemoglobin concentration and oxygen saturation that is exactly co-registered with the images that show anatomical features. Now, the last point of my presentation would be excellent anatomical, excellent functional ability in terms of photoacoustic imaging. How do we visualize molecular cellular composition of the tissue? If I look at these cells, they do not absorb. White color, although we've heard that white does not necessarily mean scattering only, there could be absorption. But in this particular case, as confirmed by the UVV studies, cells, normal cells, most of the cells will only scatter light and will have very negligible absorption. Yet our contrast mechanism in photoacoustic imaging is absorption driven. I'm out of light, but hopefully sound is still here. So how would you visualize those cells or molecules overexpressed in those particular cells? Well, the answer is you have two choices. You can go with the dye, which is much more clinically approved, or you can go with the fancier technology called nanoparticles, specifically plasmonic nanoparticles. Some of them are shown here. Right. Now, I want to sort of discuss what's better, dyes or plasmonic or photoacoustic nanoparticles. And the answer is not simple. And don't take me wrong that one is better than the other. I think they will play nearly similar role. So if I look at the sort of amplitude of photoacoustic signal versus the number of possible clinical applications, I think the intuition is very simple. The more signal I have, the deeper I can penetrate, the more diseases I can study in vivo at sufficient depths. And it happened that photoacoustic nanoparticles or plasmonic nanoparticles have much stronger absorption than any typical dye that we currently have. Right, so by following this diagram, you would say, yeah, photoacoustic nanoparticles might be a better choice. Well, there is a counter argument that one can make, and I'll make it myself. Now I put photoacoustic signal and clinical applications on the horizontal axis. But now I'm thinking of FDA, that's the US agency that will allow or disallow particular substances to be used in clinical practice. And dyes are already approved for clinical use versus nanoparticles are not. In my opinion, the time clock where it could be done probably anywhere from 5 to 10 years from now. Right, so if you're looking for clinical photoacoustic applications, then you probably will first use dyes as contrast agents before you get to the nanoparticles. However, in preclinical arena, you can use any of this as you wish. Now, there's something else that will separate nanoparticles from dyes, and that something else is called tunability, which means if I'm interested in imaging of blood, I really cannot take nanoparticles that absorb in this wavelengths. The blood will be dominant. So what I need to do is I need to take my nanoparticles and move them in terms of absorption all the way to the near infrared 1100 nanometer wavelengths. And with dyes, that's extremely difficult to do. The dyes will kind of stop at 750, maybe 800 nanometer absorption, where nanoparticles, if I make them anisotropic or I play some games in terms of composition of those constructs, I can actually make them absorb at 1064 and even slightly higher. Right, so that's one of the property of the nanoparticles that's sort of not duplicated by dyes. And the second property is these plasmonic nanoparticles do not easily photobleach. That's why we put silica on top so that they don't change any of the properties as we irradiate it with the light, versus dyes would be much harder to preserve in the same state. So there are a variety of nanoparticles one can make. This is just example from our lab, but by no means it's a all-inclusive example. You can use silver, you can use gold, you can put cast on top of it, you can put TNT mixed together with nanoparticles, so make even more stronger explosion, at least initially, to produce photoacoustic signal. You can start combining them for multimodal imaging. All of that is possible. This is example of particles that can be used for MRI, photoacoustics, and optical imaging at the same time. So one example, which I think might be the first clinical example we're going to see, because initially photoacoustic imaging will be limited to relatively superficial diseases, such as sentinel lymph node and identification of micrometastasis and such. So what I'm showing you here is the primary tumor. The physician would know the primary tumor exists. His or her immediate question would be, did this tumor metastasize? And normally, most of the tumors will metastasize through this lymph nodes or lymphatics, right? That's how it goes and get into the bloodstream and get delivered to the distant organs. Right, so the next, therefore, immediate question you would ask, having patient diagnosed with the cancer is, are there lymph nodes that are affected with the cancer cells? Are there micrometastases in the lymph nodes? And specifically, you would like to sort of evaluate the sentinel lymph node, which is the first lymph node to which the tumor is draining in this particular case, right? So, of course, that's the clinical problem, and we have solutions for that. What we normally do is inject cocktail of optical dyes that will be just for visual inspection and radioactive tracer. My laser pointer is not working. That contrast agent, bullet number 2, will be drained to the lymphatic system. And third, you will perform nuclear imaging, nuclear medicine imaging to identify the sentinel lymph node. And all you've done up to this step number 3 is you detected where that lymph node is. In order for you to evaluate whether it has cancer cells or not, you will take biopsy. And it's a relatively bloody procedure. You have to cut the skin. It's not simply injection or insertion of the needle. You will have to open it. This is where you will use optical dye to make sure where you are. You extract part of the sample and you analyze it histologically. It's very, very good procedure in terms of accuracy, but it has some limitations. And what we thought to do is, why not to use nanoparticles that could be conjugated or targeted to a particular receptor that the primary tumor overexpresses, and see if photoacoustic imaging, together maybe with ultrasound, can help. And so what I'm hoping to do here is to both visualize the sentinel lymph node, but also identify whether cancer cells are present or not. That would be the goal. So with imaging technology, I can replace the need for biopsy. So example I'm going to show you with the system that we have in our lab. It's Vivo laser. We're going to use a metastatic model, mouse model of the oral cancer. So you can see the primary tumor. We know exactly where it is. We know the phenotype. We know everything about the tumor. This is not the point of detection of the tumor. The point of this study is to be able to tell whether this tumor metastasized or not. Right? Using ultrasound, we can detect the lymph node, even the sentinel lymph node. It appears as this sort of bean-shaped structure over here. But really, from ultrasound or from any known imaging technologies, we don't know whether this sentinel lymph node has cancer cells or not. So that would be our job. I'm not going to walk you through this massive study. We're going to concentrate on this group, which is the EGFR positive tumor and EGFR targeted nanoparticles. And images I'm going to show you will be from this group. But of course, we've done excessive control, positive and negative, both ways. So with Vivo laser system, you can collect both ultrasound and photoacoustic images, right? Ultrasound images primarily will show you geometry or anatomy. You can see the skin. You can see the skin. You can see somewhere here possibly the lymph node, although this is not the best image to display that, but it more or less show you the overall anatomy. You look at the photoacoustic image, and it probably doesn't have much of the anatomical features just because it's a limited angular view, but ultrasound does help in that regard. Now remember, those images collected using the same transducer, I can just overlay them and show you what it means. So now you can see that some of the signal come from the skin. Of course, skin absorbs light. There's plenty of melanin if you wish, and generally blood vessels are there too. So there will be absorption from the skin, but what's exciting is I do see absorption from the lymph node that represent the accumulation and interaction of the nanoparticles with the cancer cells. Although that image is not what excites me, because we can collect these images at different wavelengths and actually do some processing to visualize truly nanoparticles interacting with cancer cells, and that would be the image. Now the skin was removed, not in terms of scissors, right? I didn't just Photoshop it. What I did is apply the known spectra of nanoparticles and extracted that signal only. That's the one I'm showing you on this graph, and anything else that does not belong to that was rejected in the image segmentation. And again, you can see the lymph node, and you can see plenty of cancer cells present in this particular group. If I compare the sort of enhancement of the signal before, that's the baseline, and after the injection, only in the positive group I have an enormous increase of the photoacoustic signal versus negligible, statistically insignificant increase in the other two groups. That was an example of using nanoparticles. I don't have to use nanoparticles only. I can use some functionalized or functional activatable dyes. And so in this case, same example, except we recognize that micrometastases do have overexpression of MMP, or they have MMP to begin with, which is associated with metastasis. So what I can do is I can take the optical dye that normally absorbs at 680 nanometers. But when it's activated, it does absorb at 750. I do not care about fluorescence because I'm not doing optical imaging whatsoever. So I will use that to identify where the sentinel lymph node is and whether it has micrometastasis. Right? So if I visualize dye as it is at 680, that will show me where the drainage is. If I visualize dye at 750, and if I have a reasonable signal, that will tell me whether MMP is present, which is associated with micrometastasis. So here's a 3D example, and this is just segmentation of ultrasound image to show you where the lymph node is. And those would be 3 movies I'm going to show you at the same time. One of these movies, this one, will be the view from the top, and it's MIP, which is maximum intensity projection, all of those 3 movies. The second movie will be looking from the front and collapsing all of that information. The last movie will be looking from the side. Right? Blue will indicate the dye that was just injected, and yellow will indicate dye that is activated. Right? So if we look at this image, this is more important image. You can see all of this sort of traces. This is vasculature. This is how the dye was delivered to the actual sentinel lymph node, which is this blob right over here. And again, you see this blob, this is the same over here, but we're looking from a different angle. Let me start playing it. Realize how quickly the dye disappeared from the vasculature, because it doesn't take long. I believe those movies are about 15 minutes or so. And this is initial study, so we don't have fully sort of under control everything. But the dye quickly arrives to the sentinel lymph node. It sits there for a little longer, and then it's activated as indicated by the yellow color. So that's example where you would use MMP or biologically sensitive dyes to produce images. Okay, I believe I completed my journey. I hope I was able to demonstrate that photoacoustic imaging, together with ultrasound, can visualize anatomy, physiology, functional biology. Examples are shown here. All of this were acquired either from the website or from in the lab using commercially available photoacoustic imaging systems. We can have a little bit of discussion now. I guess I'll go through those bullets quickly. Photoacoustic imaging is capable of visualizing endogenous and exogenous contrast. Exogenous comes as dyes or plasmonic nanoparticles. It's multimodal imaging technology very simply because it has ultrasound and could be integrated with a variety of optical imaging techniques. What's beautiful about photoacoustic imaging is that it's in vivo imaging technology that looking at sufficient depth with reasonable spatial and temporal resolution. Not many imaging technologies can do that. The photoacoustic signal could be highly functional. It's affected by interaction of cells with nanoconstructs. That would be either dyes or the nanoparticles. And therefore, we're not really using nanoconstructs as just contrast agents. We use them as nanosensors or nanotracers, if you wish. And because of that, we are able to visualize what I would call functional biology, which is really where the field is going, is to looking at the disease at the earlier stages when they are molecular and cellular activated rather than anatomical features did change. And photoacoustic imaging can go all the way from diagnosis to image-guided therapy and treatment monitoring. And currently we have 3 preclinical systems, but I do hope to see in the next couple of years several clinical systems introduced. With that, I will finish, and I guess I will see you all at 3:15. Thank you.